Okay, good morning to everyone. We're about to start the last speech session before the closing session, and I want to introduce you Mr. Yiannis Pavlou. Maybe you already know him from now, and he's the Academic Director of Europe for National Instruments, and he's going to present a keynote entitled Graphical System Design, a platform approach to delivering teaching, research, and innovation success in Europe. Please.
Good morning, or good lunchtime. It's great to be here again. I made a big mistake last time because Maggie was looking for me before my panel discussion to get some details about me, and I didn't serve her very well because I was hard to get to. So I took my first slide, decided to tell you a little bit about myself. So I grew up in Cyprus, which is a small Mediterranean island. I went to study aerospace engineering in Boulder, Colorado in the US, which is a beautiful place to be, and it was quite an interesting situation how I ended up there. Then I went to work for National Instruments in Austin, Texas in our corporate office. I had a variety of different roles. I tried technical support, marketing, technical marketing. I was in R&D for a while. And then of all places, I ended up in Budapest, Hungary, which is actually another beautiful place to live, where I worked more in the sales, customer-facing type roles. And then for a year, I even moved to France, Paris, France, which is, of course, another beautiful place to be. So, and then now my home base is back home in Cyprus, which kind of tells you that life is a circle. So why am I telling you all this? I think I'm trying to bias you that if you don't agree with the thesis of my presentation, I can still give you some really good travel tips, so be nice to me. So I'll tell you a little bit about the ethos, or what I think are some of the fundamental tenets that I believe in at a very, very high level. One is that the journey is the reward, which is a Steve Jobs quote that's quoted by everybody. What people don't know is that the real person that wrote this was a guy called Konstantinos Kavafis, which was a very, very famous Greek poet who wrote a poem called Ithaca, where the main principle of the poem is that the journey is, in fact, the reward or the goal. And the second, I guess my second quote was, didn't make it. So my second quote was, I don't remember what my second quote was. I think I'll move on from that point. Okay, so now I want to talk to you a little bit about platforms and ecosystems. Who here can give me a definition of what a platform is? And an ecosystem. Come on, I want to get the interaction. I know it's late in the day, late in the conference. So what's a platform and what's an ecosystem? So what is the definition of a platform? What defines a platform? Basic infrastructure that we build on, basic technology infrastructure maybe that we build on. What about an ecosystem? Ecosystem, so a collection of components that somehow work together. So I looked up a couple of definitions that, of course, I picked because I thought they fit our definition. And one from Technopedia on the platform is that it's a group of technologies that are used as a base upon which other applications, processes, or technologies are developed. So it's a baseline infrastructure upon which you build other things. And as for ecosystem, at least from a business ecosystem point of view, it's a community supported by a foundation of interacting organizations and individuals. So it's kind of like a living organism, a community of the business world. Now, why am I telling you all this? I think the whole principle of our company is founded on the idea of platform-based design. And there is an academic domain of platform-based design that is pioneered by a professor called Professor Alberto Sangiovanni Vincentelli at UC Berkeley. And it basically is based on the principle that as engineering systems get more and more complex, we have to find a way to go at a higher level of abstraction at the application level and look at an infinite exploration of the different possibilities on technology infrastructure upon which to execute it. And we need to make that mapping very, very fast so that we can go from describing an application to executing it very, very fast. And of course, a platform is the whole infrastructure by which we make that mapping and make it very, very fast because of the integration and the baseline infrastructure that's there. And our view as a company has been from the very beginning that our technology needs to work as an integrated hardware-software platform to let you go from a very wide variety of applications deployed to a very wide variety of different electrical engineering technology infrastructure in a seamless way because you're using a high level of abstraction, different models of computation, you can incorporate IP and so on and so forth. Now, taking a little bit of a detour from the platform, this is a view of how we look at our academic program serving the academic market. So we look at the different constituents, which are the educators, the students, and the researchers. And we have a number of programs, products dedicated to teaching, research, content, curriculum, and so on and so forth, and partner programs. We have a small, limited, collaborative research part of the program. And we have some resources dedicated to serving the customers, only dedicated to academia. Now, the idea is that with a single platform, we can serve the synergy or the heart of teaching, research, and innovation. And that we try to bring our whole business ecosystem to participate in the role of teaching, research, and innovation within the academic space. And there's a lot of things that we're doing to try to be somewhat unique in that area. So the elements of this ecosystem that we try to bring forward for innovation through the platform is the academic program, again, services, products, people dedicated to the academic institutions, some collaborative research. Interestingly enough, our 700 SMEs that make up our Alliance Partner program really depend on some advanced research concepts flowing into industrial applications. So we're trying to find the right programs to bind them to academia. We have a spin-off small enterprise program, so if somebody wants to do research, get to a proof of concept level, and then onboard their commercial application onto our platform, we make that happen. We're trying to bring some of our top customers into advanced research collaborative projects. We have programs to train educators, students, and researchers on our tools so that they can basically get the benefit of the platform. And of course, we're a sales and marketing company, we're industry, so we can provide leverage to some of this leading edge research, commercial spin-offs, tools, derivative products that are part of the ecosystem. And of course, at the heart of it is a platform, a technology infrastructure that we have. But all this gets built around it to really try to help create a win-win value proposition with the academic space. Summarizing the platform value, it's really getting this technology infrastructure to help hands-on practical experiential learning on the teaching side, accelerating research because we can, from a very high level, do system design to get a concept to a proof of concept demonstrator level, and driving innovation through these programs to help the commercialization of some of this technology into industry. And in each of these areas, we have some credibility, we have some success. I'm highlighting here 3 projects with very notorious European universities, EPFL. They have a project called Teaching Bridges, where they really want to upgrade their teaching through practical, hands-on learning. And they're looking at the synergy between research themes, hands-on learning, and industrial collaboration. University of Leeds have been using us for a very long time, all the way from early labs, student design, project-based design, and some of the advanced research. And Manchester University is now using a lot of the technology for hands-on student design, project design, and they're having great success in getting improvement in their learning outcomes and the rankings of the students. And we have business impact case studies for these, which are very, very detailed documents telling you what the measured learning outcome benefit has been. Now, looking at the platform benefit from a research point of view, here's an example of bringing broader ecosystem benefit to Cardiff University. They have a leading group in nonlinear microwave electronics and modeling. We kind of worked to get them on our T&M instrumentation platform for this nonlinear modeling load pool use case. And then that flowed into their spin-off and startup. And we work with our marketing organization and our sales operation to try to find big accounts that are interested in their technology. So this is a way of bringing an industry company with different parts to the ecosystem to really help research flow into commercialization through a spin-off. And this is an example of a very, very advanced research setup for RF wireless communications prototyping and test. So these are very, very expensive systems. And one thing that I would like you to think about, given the community you're part of, imagine that all these very sophisticated research systems would be available for your students to sample and look at as part of a remote online learning lab experience. Don't just think about separate teaching infrastructure. I mean, where the money is for the really sophisticated high-end equipment right now is in advanced research. There's some very exciting, exotic applications out there for that. Let's find the right online learning infrastructure to make sure that becomes accessible to teaching and to students. Okay, how do we prepare the engineer of 2030? That's a question I'm sure all of you have asked yourselves. And one observation and something that we're hearing a lot from our big industrial customers is that very complex multi-domain systems are around us everywhere. So whether you're looking at electric vehicles and the complexity that comes with that new technology and the integration of electromechanics, Red Bull Stratos challenge of somebody jumping from our stratosphere, SpaceX, commercial space exploration, healthcare technologies, elevators with the latest drive technologies, or the very, very complex technologies of a smartphone. Complex systems are with us everywhere, and technology is getting more and more complicated, so the role of an engineer and a design engineer is changing, and the design cycles are actually getting smaller. So the truth is that your graduates are going to design hardware and software components that go into systems or use them, and either way they're going to have to understand system-level design. There is no avoiding it. There is no way that they will only be experts bottom-up from the theory or one of the engineering domains, and they will not be able to get an architectural view or a top-down view of a system. There is no way they will go out in industry and be effective if they don't have a good sense of system-level design. And what are the systems of today? Well, they're integrating the different engineering disciplines: computation, computer science, controls, and communication. And of course, with that comes a lot of data management, information, big data. And there's a big shift in Europe right now towards this research domain called cyber-physical systems. In Germany, it's driving a lot of the research policy and how they expect that it will flow into real industrial applications with the Industry 4.0 consortium. And this is basically where engineering is going: multi-domain, complex systems that integrate computation, control, and communication. What does that mean from a teaching point of view? Well, it means that you have to teach the core concepts. Somebody said there's just some stuff that's core. You can't not teach them. It's the baseline by which they'll be able to be engineers. But then you have to teach them what the subsystems are, and then how the subsystems come up to a complete system from a top-down architecture point of view. You won't be able to afford not to teach them that. Giving you an example, we have a number of core courses on the bottom here: Intro to Engineering, Control Circuits, Signal Processing, Sensors, and Actuators. Then we have some domains, application domains, control systems, embedded systems and designs, a little bit of software, communications, MIMO, software-defined radio. And then it all comes together to put together an unmanned air vehicle, which is the real application, the real system, the final system. They're going to have to understand all the interactions. And it's good that they have to understand all the interactions, because it actually stitches the concepts and makes them real, and it gives a real context to them, and they actually like that. Let me give you an example. Formula Student is a very successful volunteer activity that many students do. They build these racing cars, and they go and they race in competitions. They do this extracurricular. Many of them take a year off, and they go out there and they basically design these cars to compete. Extracurricular. Most universities in Europe don't give credit for it. When I asked the students, if you could get credit for it, would you? And they said, well, I don't know, because I wouldn't want to lose this, freedom that we have to explore and look at different options and build the systems the way we want to. I wouldn't want to make this a pure learning exercise. So they're going to have to understand the system, and it's going to stitch the concepts for them and help their learning experience. Of course, we have our view, okay? So even if you don't believe or like our technology version of this, just remember by the end of the presentation, platforms, ecosystem, impact, and system design. We have our version, which is a graphical language that lets you incorporate IP from different domains, different types of tools, build a complex system, integrate to hardware. So that's our version of it. Now, one thing that we did in 1986, LabVIEW was invented, so it kind of redefined, created a graphical view for programming. In 2004, we introduced a teaching product for instrumentation and measurement called Elvis. And it basically integrated all these expensive instruments into one little device that sits on the bench for teaching with a breadboard on top. Great product for teaching measurements and circuits, very, very successful. But we built an ecosystem around that. We built a partner program around it, a number of different products, so it could be a platform for more than just measurement and circuits. In 2010, we introduced a product called MyDAC, which is a sister product to Elvis that is basically a multimeter, oscilloscope, data acquisition device in one, and it's very cheap, few $100 for a student, and it's USB controlled, and that way the student can take their practical work at home. And we have more than 10,000 of these in circulation in the last 3 years. The majority of them being used in student design or homework that's practical work. And we built an ecosystem around that. Why? Because we don't want everybody reinventing the wheel. If people can start with existing components, then they can focus on the next level pedagogical outcome, or they can focus on the next level of what's most important. 2011, we bought a company called Edis Research that builds a software-defined radio product, and we integrated it with LabVIEW, made curriculum available, and again started to build an ecosystem on that. Now, how can we go one step further? How can we redefine student design? How can we give students even better, more advanced, more flexible technologies for student design? We're National Instruments, so our version of the platform, from a manifestation of the platform design, is going to be our tool, and it's LabVIEW. And then you have to start looking at all the enabling technologies out there. And at the heart of the company, we've always looked at the semiconductor industry as a gold mine, because that's where billions of investment is going in to build technology platforms. So we need FPGA, system on a chip, microprocessor, multi-core, DSP, and we want I/O. We want all the kinds of I/O that are needed to build a very, very flexible system. And then, of course, all of this has to be very well integrated into system design. We want a student to be able to get a product and be able to use it and get a real measurement, a real interaction with the physical world in less than 10 minutes, from the time they open the box to the time they take a measurement. And ideally, it needs to be small like MyDAC, because it was very successful and more than 10,000 of them made it out there. There's new technologies, right? It has to have software on panels. It has to have thin clients, because that's the technology that all students have, and it's the future technology. And of course, it has to have Wi-Fi, because today everybody wants autonomous Wi-Fi connectivity, and we don't want long cables running around. So that's what we started with. We started thinking we need a LabVIEW programmable, all programmable SoC, rich known I/O set that can control all the different actuators, sensors, electrical signals out there, integrated Wi-Fi, compelling ecosystem, out-of-box experience is student-ready. And the product that we came up with is a product called NI MyRio, which is just released in August. It's a sister product to the MyDAC product. Again, student-centric, meaning the price has to be low enough to be accessible at least to a student, based on a platform built by Xilinx called Zinc, the most advanced semiconductor platform technology out there that we could find. It has a dual-core ARM Cortex A9, which is a 32-bit processor, 28 logic cells, 80 DSP slices, 16 DMA channels, very, very advanced technology in a single chip. And then the product, comes with accelerometers, comes with a variety of I/O resources, the same connector that MyDAC had, so that all the peripherals that were available for MyDAC, the ecosystem, gets now brought into this ecosystem. Has USB connectivity if you don't want to set up the Ethernet ahead of time. Has DC power so you could battery power it, and it can be completely autonomous. And it has space for USB peripherals so that you can get USB sticks, camcorders, and so on and so forth. And of course, from a software point of view, it has, it comes with support for all the software that we make available, and all the different toolkits, which of course we make available for teaching purposes at a very low cost. Part of the ecosystem, connectivity with Quanzer, which is a company that builds controls, plants, and actuators. And this is a connectivity device to help connect to their inverted pendulums, they're very, very advanced control devices. Some starter kits so that you have little bundles that people can get started with and get up and running for just normal electronics, embedded systems, mechatronics, and some specialty touch panel, RFID, EEPROM communication, again teaching embedded concepts. And of course we started with courseware, and we're building an ecosystem of partners to build peripherals, mini systems that can be controlled through that. All programmable SoC, very easy to use and get out of the box because we have an ExpressVI technology, which means you can use it as a measurement device just to get up and running and then start programming either the processor or the FPGA. But you can take it one layer at a time depending on what complexity you need. Extensive ecosystem, supports C and C++ because it runs Linux because of the technology that's in there, but it can support LabVIEW as well, and the interaction of all those things. Lets you integrate MATLAB script through our MathScript RT node, and that way you can incorporate IP from all different workflows and tools. But the key is that it's there to be put in the hand of the student. And you know what's interesting is when you put them in the hands of the students, what the students do with them is pretty amazing. And if you're interested to learn more about that, join us in our 2015 NI Week event in our academic forum in Austin, Texas, where you'll see the finalists of a global student design competition. There's thousands and thousands of submissions, and you'll see some really incredible things. They put MyRio out there in space. They developed an artificial heart or a pill that basically is a model of a pill that's going to get swallowed and do telesurgery inside your body. I mean, these are student projects. So that's it for me. So, don't forget the student. Don't forget getting the hands-on experience for the student. And yes, let's get all the remote equipment that's expensive and difficult to replicate. Let's get all that as well so they get a rich, real experience that they're going to face in industry.
Thank you. We've got a few minutes for some questions. Anyone? Yiannis is happy to answer.
Sorry? Yes, it's on the order of 400. It depends if it's student-centric or if it's for an institution. For an institution, it's around 400 euros for a MyRio, full-featured high end of the MyRio. There's a version without the case, which is cheaper, and there's a student version, which, like MyDAC, which is at a subsidized price by us. Maggie?
I may have misunderstood.
Yeah, what I meant is that, sorry, 10 seconds, not 10 minutes. What I meant is that it takes 10 seconds in order of taking it out of the box, plugging USB, a panel comes up and running, and basically you're taking the first measurement. 10 seconds, sorry, not 10 minutes. Yeah.
Anyone else?
Yes, sir. In August, in the heat of Austin, we have our big event. It's about 3,000 users. It's a user conference called NI Week. Within it, there's a lot of sub-conferences, research conferences in big physics or software-defined radio, cyber-physical systems. But there's an academic track, which is more for teaching, where we get a lot of our users presenting to the other users their best case studies. There's an awards ceremony, and there's hundreds and hundreds of sessions, technical sessions, as part of that. Yes, sir.
I mean, if you look at the LabVIEW product, for example, you use a proprietary plugin to get that running on a desktop machine. Now we see that more and more mobile devices enter the market. So what are your thoughts on this? Are you going to replace that by JavaScript, or what's going to happen?
You mean for a client to connect to LabVIEW or a software on panel? Yeah, we're looking at that technology. We had some discussions actually at this conference with a number of folks. I think the reality of that was that we actually took a technology choice on that front-end software on panels and thin clients that ended up being obsoleted by Microsoft. So I think we ended up going up a dead end, and we're kind of taking another route now. So you'll see a lot more coming out this year to make it cross-platform software on panels and make it much more accessible. Other questions?
I have one.
Tell me.
You presented some hands-on equipment. How does that kind of equipment links with the topics we've been discussing here with remote engineering and virtual engineering?
Good question. That's why I was looking credit at the beginning. Like, wait, why is he talking about hands-on? I think we're remoting equipment because we can't afford hands-on. So I guess I'm trying to convince the audience here of two things. One, that it's a continuum and that you do need to lower the cost of equipment, but you need to get the real hands-on practical experience to the student. And then, of course, as you go up and you get to more and more expensive equipment, we need the variety and we need the sophistication, and we need as much of that exposed to students through remote learning and remote experiments. And I also don't think they're mutually exclusive, because I can imagine taking all these student design examples, which there's 10,000 of them out there, and putting them online and letting other students experience the variety. And I think if you build that kind of platform and ecosystem mentality in the remote engineering community, then you really start to get the richness of the experience impacting the students, not re-engineering the wheel on the next IT infrastructure, whether it's Java-based or whether it's something else. So I think it's a continuum, and that a platform ecosystem approach makes a lot of sense for this community.
Thank you, Yiannis. Well, if there aren't any more questions, we'll finish this one and we'll go for the next one.